All right. How are your other classes going? Are they run, roughly speaking, like this class? Or I'm just curious if there's anything good that the other instructors figured out that I should use.
They've been pretty much the same for the most part.
What are they doing? They're using
Zoom as
Zoom
well.
and they're writing on an iPad, basically.
Yeah. A lot of them prepared slides in advance, but yeah, it's more, those courses are more like, they're better for slides.
Like what?
Math, finance, and like AI.
Those are better for slides.
Well, there's not so much like, I guess, math that you do like on the spot.
Uh, and you have a class that's what's the AI class actually? What is it called?
1510. It's new this year.
And it's
It
what is it? It's in the it's in the computer science department.
No, it's math.
Oh, it's in the math department.
Yeah.
So who's teaching that?
Papillon.
Papillon?
Papillon. Papyan, I believe. That's how you spell it.
Papyn?
Yan.
Yan.
Yeah, I believe that's how you spell his name.
And so what are you doing in this AI class?
So far, he just went over like different types of networks, and then we talked about some phenomenon that happened with them, and like some adversarial stuff. And now we're getting into more like the mathy side of it, like regression and stuff like that.
I see.
Yeah.
And is it what do they do in terms of streaming and recorded lectures? What do they are they doing YouTube streams or something else?
He is actually doing exactly the same as you now. He started on BB Collaborate, but it didn't work out well.
Yeah, well,
So
garbage software. Okay.
yeah, so he switched to Zoom. Yeah,
Right. That's right.
he switched to Zoom, and he hasn't been live streaming on YouTube, but he posts them on YouTube.
I see.
So I guess he like pulls them from Zoom somehow and then posts them after.
Right. Interesting. I'd like to take a look. What is the? Could you post the link to his stream?
Sure. I think they're available to everyone. I can just post a link to his website, and then his streams are on the bottom.
I see. Oh, you like the microphone. Neo likes my microphone. I'm not even using my good microphone. I'm using the sturdy one. This is the sturdiest microphone you can find. An SM57. It's ages old. It's a very old model, but very dependable.
His links are at the bottom there.
Okay, yeah, thank you.
No problem.
I actually bought a microphone that arrives today because of this class.
Oh. Well, I hope you didn't spend too much because this microphone is not very expensive. Yeah, SM58 is the other one I was thinking of. I just like the sound of the F57 a bit more for certain instruments. But SM58 is probably even better for interviews. Okay, any questions about what we've been doing so far?
Can I ask a question? I guess maybe at the end of the lecture, could you just give us a bit more information about the quiz, and when it's coming up and stuff like that? So I think there's a bit of conflicting information. Like some people have been saying, well, on the syllabus it says it'll be in class about the lecture that just happened, and then I think some people were saying that the quiz will be about the reading that's assigned in the assignment, and I just want to know, like, which.
Yeah, the reading will happen. The first assignment is due on when is it? Thursday night?
Friday.
Friday. So it's due on Friday night?
Yeah, yeah.
Okay, well,
It didn't specify what time, but it just said February 5th. Yeah.
February 5th. Okay.
Which is Friday. Yeah.
Well, halfway through the class on Friday, we'll have a 10-minute quiz. It's a multiple choice quiz based on the reading and the material in class. It's basically I'm not trying to make it difficult. I'm just trying to make sure that it's a signpost, so that you're kind of up to date on the material. That's all.
All right.
So I think the most important thing would be to know to know the material that's in the notes up to this point, the material that was in class. It's a 10-minute quiz, so I'm not going to be asking you to do calculations and so on. Is that okay?
Yeah, okay, that sounds good.
Okay, I think we can start. Okay, I'm going to continue along the line that we started talking about before. So I'm going to talk about combination of systems by tensor product. So I will discuss the tensor product. Before that, I just want to just make a little bit more explicit a tool that we're going to use constantly, and this is the relationship between Lie algebra and Lie group. Okay, so let me use as a first example the group of rotations. Let's say three-dimensional rotations. This is a group with the name SO3. So this consists of, so SO3 consists of matrices, 3 by 3 matrices, such that X transpose X is equal to the identity. Okay, this is the condition that it is an orthogonal transformation. But if I wanted to preserve orientation, I need its determinant to be positive rather than negative. I want the determinant to be 1. Okay, so for example, this would be an example of a three-dimensional rotation which fixes the z-axis. So it's a rotation in the xy plane. Okay. So this is an example of a Lie group. So this is obviously a group. If I, under matrix multiplication, but it's also a smooth space. It's a smooth manifold. A smooth manifold. What I mean by that is that you could think of it in these terms. You could say that you could think of the entries of the matrix as a vector in a 9-dimensional space. And in that 9-dimensional space, the vector has to satisfy a bunch of equations. This, you could think of it as being a whole bunch of equations. If you write them out entry by entry, and this will be another equation. So you could say, well, how many equations are there? Well, you could analyze it one way. The naive way of answering it, which is going to give the wrong answer, is that you could say that this is a point in a 9-dimensional space, and it satisfies 9 equations, because this identity it has 9 entries. And so if you compute X transpose X, that will be a matrix with 9 entries. And if you set those 9 entries equal to these 9 entries, then that's placing 9 equations on the 9 unknowns. And then you go ahead and put a 10th equation. So it looks like you have 10 equations in 9 unknowns. So it looks overdetermined. All right, but the right way to analyze this is to see whether there are any constraints that happen to be satisfied automatically. So, for example, here, if I look at this matrix X transpose X, I notice that it's automatically symmetric. If I take the transpose, it's equal to itself. So this is a symmetric matrix. Okay, and so what we have is really, we really have this X transpose X quantity is really a map which goes from 3x3 matrices to symmetric 3x3 matrices. Now, symmetric 3x3 matrices only have, there's only 3 of the entries are dictated by the other 6. And so it's really just a 6-dimensional space of symmetric matrices. So I'll say matrices, because we have A, B, C, D, E, and F. There's only 6 independent variables. And the identity is a point in that 6-dimensional space. And what we're looking at is the preimage of this identity element. So it's really just 6 equations in 9 unknowns. Okay, and then we notice that that the determinant of X transpose X is the same as the determinant of X squared. And this X transpose X is equal to the identity, so it's equal to 1. And so the determinant of X has to square to 1, and therefore the determinant is, a priori, it's just plus or minus 1. So this equation here is just picking out 1 versus minus 1. So it's not really imposing an additional equation. It's just picking, half of the matrices that satisfy this equation. So really, this is just 6 independent equations in 9 unknowns. That's all. And so you end up with a three-dimensional space. And so this manifold is a manifold of dimension 3. Okay, so how do we check that it's smooth? Well, you probably learned that already in multivariable calculus, that if you write a polynomial equation for a surface inside a flat space, you can check by computing the derivative of that polynomial. You can check whether that surface is smooth or not at every point, right? So if the function has a critical point, so if the derivative vanishes, then there's the possibility that it's singular at that point. And so what you can check by taking the derivative of these equations, you can check that the thing that it cuts out is smooth. And we're going to do part of that calculation in a second. I just want to, so now's a good time to move this down and give an example 0. And then we'll get back to this example. The most important example is the group of two-dimensional rotations. SO2, and this is sometimes given the name U1. So it's, you could either think of it as, in the same way as before, it's really all of these 2x2 rotations. But you could also think of these as unit complex numbers. So you could think of them as 1x1 complex matrices, such that Z conjugate transpose, there's no transpose here because it's just a single number, times Z is equal to 1. So it's easy to draw this group as a subset of the complex plane. And so that's what the group looks like. It's a group. Obviously, if I multiply two matrices this way, or if I multiply two unit complex numbers, then they will result in a unit complex number. So they form a group, but they also form a smooth space, which is just a curve, a smooth curve inside the plane. Okay, now all right. So what I want to focus on is the idea of a, I want to focus on certain paths in this group that begin at the simplest element, the identity element. So let's say that we have a family of complex numbers. So just imagine T is in the real line. So we have a family of complex numbers such that Z of T is of unit norm for all T. So this is a path in the circle. Okay, and I want at T equals 0, I want this to be the unit element of the group. All right, and then I want to compute what the tangent space to the identity element is. So this is a path that it's passing through this identity point at T equals 0. So what I'd like to do is find the velocity vector of the path, the tangent vector of the path at t equals 0. So if I differentiate this thing, I'm going to get this equation. So taking time derivative, I'll get this equation. And if I look at this equation at z equals 1, what that tells me is that z bar dot, or in other words, this z dot, this whatever this tangent vector is, it satisfies the condition that the complex conjugate plus z dot is equal to 0, or in other words, z dot is pure imaginary. And that's not too surprising because because the tangent space to the identity of U1 is exactly a line that's pointing parallel to the imaginary axis. And so it makes a lot of sense that the derivative at the identity of this path will lie in the imaginary reals. Okay, now for 3D rotations, we can do the same thing. We can imagine that 3D rotations are some kind of three-dimensional space that's somewhat like a circle, but of higher dimension. And in this space, we have a special unit element. I'll call it by I. Okay, and we would like to know what is the tangent space to this group at the identity element. So this is the tangent space to SO3 at the identity element. So how do we do this? Well, again, we can assume that x of t is a path, a smooth path. It's a family of matrices where every matrix entry depends on t smoothly, such that x of t transpose times x of t is equal to the identity for all t. And the determinant of x of t is equal to 1. And then we take the derivative, d by dt, at t equals 0, x of t. This will be what we normally call x dot of 0. So if I differentiate this, what I'll get is x is equal to 0. And this is just 1, the identity, I mean. So is this one. So I end up getting that the tangent space to the identity element of this group, SO3, consists of, I'll call this x dot A. It's the set of A 3 by 3 matrices such that A transpose plus A is equal to 0. Or in other words, it's the skew symmetric 3 by 3 matrices. And in other words, it's of the form A, B, C, A, B, C. Okay, so the tangent space is a three-dimensional space. So we get a 3D tangent space. Okay, so Any questions about just this? I mean, we're going to go more into this theory in the next page, but so far I'm just defining some simple groups which happen to be subsurfaces or subvarieties, submanifolds of flat space, and I'm computing their tangent space at a point. Any questions about this? Let me do one more before I kind of explain why we're focusing on this. So the unitary group UN, it's the set of n by n complex matrices, but they satisfy a condition that involves complex conjugation. U bar transpose U is equal to 1. And SUN is the set, it's UN intersect determinant equal 1. So it's just the requirement that the determinant is equal to +1. Okay, so if I wanted to compute the tangent space to the unitary group at the identity, I would look at I would look at a path which is passing through the identity U of, so this should be a path in UN with U of 0 is equal to 1. And I should have that U of t is equal to 1. And if I differentiate this, then I would get U dot bar transpose times the identity plus the identity times U dot is equal to 0. Or in other words, U dot transpose bar is equal to minus U dot. So in other words, U dot is skew adjoint. This is the way it's normally called. So when you take conjugate transpose, that's called an adjoint. And this is the condition of being skew symmetric, but in the adjoint sense. So it's a skew adjoint matrix. So for example, if we take n is equal to 1, this will be a 1 by 1 complex matrix. And we'll just get z bar z is equal to 1. And we'll get that z dot bar is equal to minus z dot, which means that z dot is pure imaginary. So being skew adjoint and being pure imaginary 1 by 1 matrix, it's just a special case. So this is why U1, the Lie algebra, the tangent space to the identity of U1 is IR. The tangent space at the identity of U2, right, is the set of matrices which are skew adjoint. So if you're skew adjoint, that means that your the diagonal entries must be pure imaginary. And the off diagonal can be anything as long as you'll get its minus conjugate will be on the bottom left-hand side where alpha is in C. Okay, and right. Any questions about this so far? All of the groups that I've discussed so far are examples of compact groups. Just because if you look at the equations, just because they're closed and bounded subsets of Euclidean space, right? Because they're defined by an equation, so they're closed in the topology of Euclidean space, but they're also bounded. And the reason they're bounded is should be obvious, because if you look at this equation, x transpose x equals the identity, it basically means that the norm, the sum of the squares of the entries of x all equal 1. So that means that they all lie on a huge sphere, right? The entries of the matrix cannot get very large if it's to be a rotation. And the same thing goes for unitary. The unitary, this is just the complex version of rotations in a way. This is basically the sum of the square norm of the entries of the matrix. And so that means that the norm of any given entry can never exceed, whatever 1. And so the matrix in c to the n is limited. It's bounded. It cannot escape off to infinity. There are many groups for which this is not the case, but the compact groups are the most important ones, and they're the ones that we're going to. And of course, these groups have a nicer description in terms of the inner product, right? We know that this can be written as the set of linear transformations, such that so we don't need to think of them as matrices. We could just think of them as linear transformations which preserve the inner product, the Hermitian inner product. And similarly here, instead of this equation, we could say that it's the linear transformations of R3 such that it preserves the Euclidean inner product. Okay, it's just useful to have. It's useful to have the matrix description just so that no one gets confused. So we have skew adjoint and skew symmetric matrices. Okay, now, all right. So the reason that I'm focusing so much on this tangent space to the identity is because the theory of groups is really governed by these tangent spaces. So the definition, if G is a Lie group, this means that it's a group which is also a smooth manifold, where the group multiplication is smooth. And for us, the fact that they're smooth is, like I said, it's a calculation that involves checking these polynomial equations inside Euclidean space that these things satisfy. But if G is a Lie group, then its Lie algebra is by definition the tangent space to the identity of the group. And it's usually denoted with a math frac G. All right. And the main thing the main thing to know about this is that there is an exponential map which maps from the Lie algebra to the Lie group. And for matrix groups, like the ones that were just above, these are groups of matrices. This is just the matrix exponential. So let me do some examples. So we have for U1, actually, this is the 0th example. The U1, which is the Lie algebra of U1, is just IR. And e to the I theta, for theta in R, we know that this is in the unit circle. So this means that we have an exponential map from IR to U1. U1, you could either write it as U1 or as S1. Okay, and what this thing is doing is it's just taking the line right, and wrapping it around the circle. And so you can see that the exponential map is not an isomorphism, of course, because it's between the tangent space, which is a vector space, and the group, which is definitely not a vector space. But this exponential map is a local diffeomorphism at the identity. So in other words, it looks like an isomorphism only near the identity, but then eventually it fails to be an isomorphism. Let's do another example. So if X transpose equals minus X, if this is skew symmetric, then e to the Tx, where T is in R, that this is a path in SO3. So e to the Tx, I'm assuming that you've started doing the assignment, so you know what this is. This is 1 plus Tx plus T squared over 2 factorial X squared, and so on. This thing, if I take its transpose and I multiply by it, then you can see that taking the transpose of the exponential is the same as taking the exponential of the transpose. So this will be e to the Tx transpose e to the Tx. And so it is definitely not true that e to the A, e to the B, yeah. Yeah, so yeah, we're not doing the so it is, let's see. So it is not true that e to the A, e to the B is e to the A plus B in general. Because of course, if this were true, then this would be equal to, this would be equal to e to the B plus A, right? And this would be e to the B, e to the A if it were true. And we know that matrices don't generally commute. Okay, so this is not true generally. However, if A and B commute, that means that they behave like numbers do. And the formula for the exponential holds just like it always does. So then e to the A, e to the B is equal to e to the A plus B. Okay, but now take a look at the equation above. We have e to the X transpose, e to the X. But what do we know about X and X transpose? We know that X transpose is equal to minus X. So that means that X transpose is just e to the minus X. This is just e to the T minus tx e to the tx. So definitely x commutes with x commutes with itself. So this will definitely be e to the x minus x, which is just e to the 0, which is just the identity. So we have that that this is a rotation. Okay. So in general, if you want to generate a rotation, what you should do is pick a skew-symmetric matrix and exponentiate it for some time, and that will give you a rotation. So so this shows us that e to the tx is a path in SO3 starting at the identity, and not only is it a path, but it's very much like the flow that it is exactly like the flow that we studied, in the sense that if you look at the value of the path at a t1 plus t2 time, this will be e to the t1x, e to the t2x. And so you have this nice group property. This is called a one parameter subgroup. Okay, but it's a path. Okay, and it's a path whose derivative at t equals 0 is x. So this is giving you a way of generating paths inside this nonlinear space inside the Lie group. And finally, and this is the one that's the most important for us, is that if A or if if A adjoint is equal to minus A, then e to the ta is in UN. And we get a one parameter subgroup of the unitary group. Okay, so the same argument holds, that we can check that this thing is in the unitary group. So this is exactly how this is, you know how from a practical point of view, when you try to describe rotations, you usually say, this is my axis, and then I want to rotate a certain angle about the axis. Okay. So what I'm describing here is a vast generalization of that idea. The choice of the axis is the choice of the Lie algebra element. It's a choice. So this is like, let me draw a picture, I guess, to indicate this. So this is the group. This is the identity. This is the tangent space. This choice of a tangent vector, that's like the choice of the axis of rotation. Of course, these are more general than rotations, but it's the basic idea. And then what happens is that you exponentiate for a certain amount of time to get the actual rotation. And this amount of time is the angle of rotation. So you can always obtain these transformations or I mean, you need to be a little bit careful. The group might be disconnected. The group might have two pieces like this. And so when you exponentiate these Lie algebra elements at the identity, you will only be able to get paths which are connected to the identity. You will never be able to, produce a path that jumps over to the other connected component of the group. This exactly happens in the case of the full orthogonal group, because the determinant can be +1 or -1. So you're never going to be able to get a rotation with determinant -1 starting with the identity and exponentiating some axis for a certain rotational angle. Okay, so yeah. Any questions so far? Exponentiation of Lie algebra elements to Lie group elements. You got to have at least one.
So the Lie algebra is in the tangent space of the group.
It is the tangent space of the group at the identity. Yeah, that's what it is. Did I already explain what a Lie algebra is? I did, right? Okay, so the remarkable fact, well, okay, I mean, we can, this is in the reading anyway. So the Lie algebra, which is the tangent space to the group at the identity, it inherits a bracket which is skew symmetric. It's bilinear, skew symmetric, and it satisfies the Jacobi identity, which means that the bracket of A, B with C is A, is A, B, C minus B, A, C. And, right, and the way that this works is kind of interesting. What you do is you so this bracket, it basically this bracket measures the failure of group elements to commute. Okay, so if you were dealing with a group, all of whose elements commute, then this bracket would be 0. The bracket of any two things, A, B, would be 0. So how does this thing work? Well, it's pretty simple. So let X and Y be elements of the Lie algebra. These generate one parameter subgroups, e to the tx and e to the ty. So these are paths in G. And then I can measure whether they commute with each other by doing the following. I can take e to the tx, e to the ty, e to the minus tx, e to the minus ty. Okay, notice that if x and y commute, right, then these all cancel out. I could bring this over to this side, and then they would cancel, and then the y's would cancel. Okay, so, and what you can also see is that at t equals 0, So let's say this is the identity. At t equals 0, this is the identity, and so are these two. So at t equals 0, this path begins at 0. So it begins at the identity, sorry. So let's call this gamma of t. Gamma of t is a path in the group starting at the identity. And this path measures the failure of x and y, of x and y to commute, or of e to the, it really measures the failure of e to the tx and e to the ty to commute, right? This is called, this expression is called the group commutator. It's the analog of x, of ab minus ba, except for the group multiplication, matrix multiplication. Instead of doing AB minus BA, you do AB B inverse A inverse. AB A inverse B inverse. So this is it's basically measuring the failure of these group elements, these two group elements to commute. Okay, and well, okay, the nice thing about this is that we can differentiate this thing at t equals 0, and we can get a tangent vector to the identity. This is gamma dot. And so that way we can take, as an input x and y, those are tangent vectors to the identity. We can exponentiate them to one parameter subgroups. We can commutate them, and then we can differentiate the result. And that result will be the Lie bracket. Okay, except that there's one little lie that I told, which is that the first derivative turns out to be 0. It's kind of surprising, maybe not. But no matter, let's take the second derivative. This is, by definition, the Lie bracket of x and y. It's the first non-zero correction to the commutativity. You see what I mean? Like, if they commuted, then this would just be a path that is stuck at the identity for all time. But because they don't commute, this path will move away from the identity. But to first order, they commute. And then to second order, that's where they fail to commute. And that thing that measures that failure is the Lie bracket of x and y. Okay, and it's an interesting exercise to check based on this definition. It's just a simple calculation that the Jacobi identity holds. But you see what I mean? That this thing measures the failure of x and y to commute. Yeah, and I should say that yeah, and I should mention right away that that for matrix groups, this is just the usual commutator that we know. So let me just give some examples. Right? If x transpose is equal to minus x, right? So if this is a skew symmetric matrix, and if y transpose is equal to minus y, then if I take the commutator x and y, and if I take the transpose, this is just xy minus yx transpose, which is y transpose x transpose minus x transpose y transpose, right? which is minus y minus x minus x minus y, and the minuses cancel out, and I just get yx minus xy, which is minus xy. Okay, so this special subset of the matrices, namely the skew-symmetric ones, they form a Lie algebra under a commutator. So this is called SO3 or SON, the Lie algebra of, so if I take SON, which is just the tangent to the identity of SON, which is just the set of X transpose equals minus X skew-symmetric matrices, and if I take it together with the commutator, this is an example of a Lie algebra. This is the Lie algebra of the orthogonal group. Is this first example okay? Skew-symmetric matrices closed under commutator. Notice that if X and Y were symmetric instead of skew-symmetric, then if you look at this computation, the commutator of X and Y would be this, but then here I would have a plus, 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 plus. That wouldn't be any different, and I would get this, and I would still get this. So if X and Y were symmetric, then their Lie bracket, or their commutator would be skew-symmetric. So that means that the symmetric matrices are not closed under this bracket, and the symmetric matrices are not a Lie algebra. They are not the tangent space of any Lie group. They don't have the Lie algebra structure. Okay, the next example is the important one for quantum mechanics. It's if X is skew adjoint and Y is skew adjoint, then X bracket Y will be just minus the commutator, just same argument as before. So that means that skew adjoint matrices are closed under commutator and form a Lie algebra, the Lie algebra UN, which is the Lie algebra of the group UN. Okay. So now there's a confusing annoyance which has to do with conventions in the community, which I want to discuss right now. It has to do with, okay, I'm going to ask you guys a question. So we talked about the skew-symmetric matrices inside all matrices. My question is, what kind of a subset is that subset inside the matrices? The subset of skew-symmetric matrices is what kind of a subset of all n by n real matrices?
Vector space?
It's a vector subspace, right, of the space of all matrices, because the sum of skew-symmetric matrices is skew-symmetric. Everyone sees that, right? 0 is an element there. 0 is skew-symmetric. If you exponentiate 0, you're not going to rotate at all. It means that you're choosing no axis and no rotation. Okay, now what about this one? What if I look at the skew adjoint matrices inside all n by n complex matrices? what kind of a subset is that subset? Someone else?
A real vector space, but not a complex one?
Yes, it's a real vector space, but not a complex one. So UN inside C n cross n is a real vector space, vector subspace. Okay, because if I multiply x by I and I take its adjoint, okay, what do I find? I find that I get minus ix bar transpose, which is minus I x adjoint. If x adjoint is minus x, this will be ix. So you see that if I multiply something skew adjoint by a scalar, and if that scalar is imaginary, then the result is not skew adjoint, it's self-adjoint. Okay? So, right. So the way you should think is that the space of matrices is a, let's say, n by n complex matrices is a vector space, which has a complex structure, multiplication by I, okay, is acting on it, and this thing has inside it a subspace, say through the origin, and these are the skew adjoint. Okay, but if I multiply the skew adjoint by I, right? If I take any skew adjoint element x, let's say x is in here, right? Then ix is going to lie not in the skew adjoint, but in the self adjoint, which is complementary to the skew adjoint. You can't have a matrix that's self adjoint and skew adjoint unless it's zero. So ix would be located there. Okay, so you see that multiplication by I is a transformation that maps the skew adjoint subspace to the self adjoint subspace. And both of these are, of course, because they're not stabilized by multiplication by I, they're not complex subspaces, they're real subspaces. Okay, so this complex vector space of n by n matrices has a natural decomposition into skew adjoint and self adjoint. So if you take anything in here, let's say t, let's say, then you can write t as t plus t bar transpose plus t minus t bar transpose over 2. Right, and then you can write it as a direct sum, right, of skew adjoint and self adjoint components. So any n by n matrix can be expressed as a sum of a self adjoint and a skew adjoint. You see what I'm saying? But in order to do this, we needed to use the complex conjugate, which is not a complex linear operation. Okay, and right. Okay, and if we want to go back from the self adjoint to the skew adjoint, we multiply by minus I. That undoes the multiplication by I. Okay, so this is the thing that physicists do. What physicists do all the time, and for good reason, is that they think of the infinitesimal symmetries of the Hilbert space or of the quantum system as being Lie algebra elements of the unitary group, because the unitary group it preserves this natural inner product that we use to get our probabilities. So the unitary group are the transformations of the quantum system that preserve all probabilistic information. Now, for the infinitesimal transformations, they take the tangent space to the identity of the unitary group, and they should get skew adjoint matrices, but instead they represent them as self-adjoint matrices, because self-adjoint and skew adjoint are isomorphic by multiplication by I. Okay, so and the other thing that's good about self-adjoint matrices is that self-adjoint matrices have real eigenvalues, whereas skew adjoint matrices have pure imaginary eigenvalues. And so everyone prefers for things to be real, and so that's why self-adjoint have a privileged position in quantum mechanics. Yeah. So let's look again at let's look again at.
I just want to say,
Oh yeah, sorry.
10 minutes over time.
Oh, say again.
I think we're 10 minutes over time for the lecture so far. Like the lecture ends at 2 o'clock.
Does it?
Yeah, pretty sure.
The 2-hour one is on Wednesday?
Friday.
On Friday. Oh, right. It's Wednesday. Yeah. Okay. Yeah. Sorry.
I'll be happy to continue on. I just have class right now.
Okay. Yeah. Sorry about that. Let's stop now. And that's good so far. We've discussed exponentiation, Lie algebra, and the fact that the self and skew adjoint are related by multiplication by I. I'll continue off this on Friday. Sorry about that. I'll stick around now for office hours, but I won't continue the material. Yeah, questions?
I have a question. When we only differentiate at the identity element,
yeah,
does this kind of would that end up capturing the tangent space in some sense of the entire group because of some kind of symmetry?
Yeah.
What
So
if you have the tangent space a different element of the group?
well, okay. So let me answer your question. It'll take me a couple minutes. So let's say that G is your group. Let me draw it here. G. There's the special point, the identity. Okay. So we have the tangent space to the identity, which is little g. So far, so good. Suppose that we had another point in the group, a general point G. Okay. So my first question is, how do we get from the identity to this element, little g? How do we travel from the identity to this group element G?
Plus G.
Say again?
You just add G, I guess.
You can add G to what?
To the identity element.
Okay,
No,
that's right. But let's say these are matrices, right? So this is this is the identity matrix, and this is some other matrix. How do I get from here to here? Do I add? I do like I plus G?
Oh no, you multiply. Sorry.
You multiply.
Just the operation. Yeah.
You use the group multiplication to multiply. So you go from I to G by multiplication, right? That's what you said? So what's the operation? The operation is that you multiply by G. So if you multiply by G, So let's talk about an operation which is multiplication. I'll call it mg, multiplication by g. What does this act on? G is fixed. Multiplication by this element, what does it do?
It not only moves the points around, it also push forward to a diffeomorphism.
Don't tell me what it not only does. Tell me what it does. In other words,
So
I asked you, what does this act on? Multiplication by G maps what to what?
The group to itself.
Okay, so this maps the group to itself. And let's say I need to take now a general element of G, H. Where does it send H?
H times G.
H times G. Well, what about G times H? Does it send it to G times H or to H times G?
I guess you have to pick one. I'm not sure. It's
Yeah,
not doesn't necessarily commute.
They don't commute, so I'm asking which. That's why I asked. If they commuted, I wouldn't have asked the question. So which one is your multiplication by G sending H to? I think it's very interesting. It's interesting that you could conceive of this map and even know a lot of things about it, even without knowing how it's defined. Because you don't know where any point is sent. H is sent where? HG or GH? Does anyone have an idea?
It shouldn't matter, right?
Doesn't matter.
I mean, you're going to get the same thing. If you do left multiplication, then whatever. Like, I feel like you'll get the same result.
There is clouds forming above your house right now. Clouds forming, darkness, lightning. Be careful. The left action by G and the right action by G are very different. And we would not have matter if that were not the case. We would not have the strong force because it's based on SU2, SU3. The whole thing is based upon the fact that these don't commute.
No, I agree that they don't commute, but I feel like whatever statement we're trying to make.
If they don't commute, that means that this map is undefined, right? So it makes a big difference. So the answer is that there are two maps, LG and RG. Left multiplication by this fixed element, and we also have RG, which is right multiplication by G. So this one will take H to GH, and this one will take H to HG. No big problem. There's just two maps. Are you still with me, Neo? Okay. So, and now this thing is a map from G to G. So what kind of a map is it? What can you say about this map, LG? Let's focus only on one of them. Let's focus only on LG. What kind of a map is this from G to G? Most obvious thing you could ask about it is whether it's injective, surjective, bijective.
Should be a bijective map.
Why?
Because you could just add its inverse. Sorry, you could just multiply by its inverse. That's the.
So what is the inverse of LG?
LG inverse, like LG's inverse.
Absolutely. So LG inverse is equal to the identity on G. The identity on G. Not the identity of G, but the identity on G. Okay, so it's a bijection. What about smoothness? Is it smooth? Left multiplication by this fixed element, is it a smooth map from G to G? The answer is yes, because we're assuming that the multiplication is smooth. The multiplication as a map from G cross G to G is smooth. So if we fix one of the entries, one of the arguments, that will still be smooth. So what we have here is a smooth map with a smooth inverse, which is called a diffeomorphism. It's as good a map as you could possibly imagine. It's a bijection with a smooth inverse. Okay, and okay, great. So that means that we can differentiate this map, and it will give, where does this map take the identity? It takes it to little g, and therefore we can differentiate LG, and the derivative will map from the tangent space at the identity to the tangent space at little g. So let me draw the tangent space at little g. Okay, and this differential is an isomorphism from the tangent space at one point to the tangent space at the resulting point, and this would be true for any point, right? You could go from any point. You left multiply by g, and that would say that the tangent space wherever you started would be identified with the tangent space wherever you end. So this is a very special fact about groups, Lie groups. What people say is that they are parallelizable. This means that if you this means that all tangent spaces can be identified in a uniform way. Are naturally isomorphic. So in other words, the tangent bundle of G is just G cross the Lie algebra. Okay, but the tricky thing about this is that it's parallelizable in exactly two important natural ways. In two different ways. You could either go on the left or you could go on the right. It's like people. You can have left-handed or right-handed isomorphism trivializations or parallelizations of the group. Does this help? Does this answer your question? So one of the cool things that you can do is you can amuse yourself by going to G using the left translation by G, and then you can come back, but instead of taking the same path back, instead of left translating by G inverse, you could right translate by G inverse. So a kind of interesting question is what happens when we take what happens when we left translate by G, but then right translate by G inverse? This will also take the identity to the identity. Okay, and if we differentiate this thing, it will take the Lie algebra to the Lie algebra. But this will not be the identity operation. This is an interesting map. So anyway, by playing off the left and the right translation, you can do a lot of interesting operations on the group. This is a well-known operation, this thing. What is it?
Conjugation.
Yeah, it takes any group element and it left multiplies by G, right multiplies by G inverse, so it's conjugation by G. So it happens to fix the identity element, but it doesn't fix other elements. There's other elements that would not be fixed by this operation. And so you can think of it as doing an operation which is kind of rotating the group with the identity element as a fixed point. So this conjugation by G fixes the identity, but it moves G around. And you can see that the tangent space to the identity will be affected somehow, right? Because we're rotating with the identity as a fixed point, but the tangent space will move. And there will be a linear transformation on the tangent space, which is exactly this. It's exactly, it can be obtained by differentiating the LG RG inverse. And this whole transformation is called big add of little g. It's a linear transformation on the Lie algebra, which is called the adjoint action. We're going to study this in not this week, but next week, or maybe the week after.
Could I ask a question or?
Yeah, go ahead.
Okay. Mine is more so kind of about the assignment because I'm still a little bit lost with like coordinates and everything.
Okay.
So number 1C, this is the one about like the sphere. So I guess I'm still a little bit confused of what exactly is the inner product versus like the normal phase space point. Like I guess just the notation is throwing me off a little bit. So for example, are we setting Q1 equal to X1 and Q2 equal to X2? Or
well, it says use Q1, Q2 as coordinates. So Q1 and Q2 are supposed to be some coordinates. And the question is, which coordinates are they? And what I'm asking you to do is use X1, X2. So X1 and X2 are defined, right? If I tell you X1 and X2, you can figure out, sorry, I just want to see here. What is it? X1, X2, X3. Yeah, so I'm saying that away from X3 equals 0, you can coordinatize the sphere by just these 2 points, right? So if you know X1 and X2, then you can determine what X3 is. Right?
Kind of like theta and wait.
It's basically just think of the upper hemisphere.
Okay.
Right? The upper hemisphere, you can just flatten it down to a disk in the plane. And so that's just telling you the X and Y coordinates of a point there. So if you know the X and Y coordinate inside the disk, there's going to be exactly 1 point on the sphere above X1, X2.
Okay.
There's going to be also exactly 1 below. So you just need to specify first, okay, I'm working on the top hemisphere, and I'm going to use X1, X2 as my 2 coordinates. If I know X1 and X2, I can figure out which point on the sphere I'm at. So it's a coordinate system on the upper hemisphere, yes?
Okay.
Yeah. So then the question is, that's a configuration space, and Q1, Q2 are configuration space coordinates. And whenever you have a configuration space and you choose coordinates on it, then there will be automatically canonically conjugate coordinates which measure the momenta of those coordinates. So it's only after you pick the coordinates on the configuration space that you get coordinates on the cotangent bundle of the configuration space. So that's the reason why I fixed what the Q's are. Once the Q's are fixed, then the P's are determined by the Q's.
Okay.
Confusion, right?
Yeah, a bit, but
okay. So let me just let me just review the train of logic.
Okay.
So if we have a configuration space with coordinates q1, qn, okay, this means right away that the tangent bundle, the tangent spaces, have a basis d by d q1, d by d qn. Okay, so when I choose a coordinate, I automatically get unit vectors, or not unit vectors, but basis vectors for the tangent space to the configuration space. Okay, and this automatically means that I get a dual basis for the dual tangent space, which is called the cotangent space. So that's going to be dq1, dqn. Okay, so all I'm saying is that when you choose a coordinate system on the configuration space, you get a basis for the cotangent space.
Right.
Okay, and what is the cotangent space? Well, the cotangent space is a vector space at every single point of the configuration space. So if the configuration space looks like this, then every single point will have a vector space associated to it, which is the cotangent space. Let's say the configuration space is called big Q. So big Q, at every point of it, it will have a tangent space and it will have a dual space to that. And that's the cotangent space. And so this will form what's called a bundle. It's just like a bundle of vector spaces, one vector space for every point in the configuration space.
Wait, so the dual, would that be kind of like parallel to the configuration space, or what exactly? In the picture, where would the dual be?
I tried to draw it here, the dual.
Oh, okay.
This,
so then which is the tangent one? Would it be?
Well, I'm not trying to draw a geometrically realistic picture. I'm not drawing, like, if I had to draw the tangent space, I would draw it the same way. I would draw it like this.
Okay.
This is TQQ. I mean, of course, the tangent space is tangent to the points, but I'm now going to just separate it out and just stick it like on top of.
Okay.
Just to indicate that I want to, it's basically, you could think of it as a family of vector spaces, which is parametrized by the point in Q. And the relationship between these two is that one is just the dual of the other. That's all. Okay, so, but here the thing is that I have a basis here of each one of these. I have a basis, which is dq1, dq2, right? And then along the, so now think about what's happening. So now this space is larger. It's twice as big, because if I'm at a point here, I could either move in the q direction, which means I have to change my point where I am in the configuration space, or I change which covector I'm at that point, right? So that means that there will be n degrees of freedom in the horizontal and then n degrees of freedom in the vertical, okay? And the point is that because the vertical is a vector space and because I have a basis, that means that I automatically have a natural coordinate system here because I have a basis. So I just expand any point in terms of the basis and I will get n coefficients for that. So if I have a general point here somewhere, right, I would say that this point is at q equals q1 qn, and in terms of the basis is p1 dq1 plus pn dqn. So in total, it has coordinates q1, qn, p1, pn.
Mhm.
The q's tell you which point of configuration space you're at, and the p's tell you which combination of the dq's this vector, covector is.
Mhm.
Okay, and so this is the key point, is that the whole coordinate system is determined by the choice of the q's only. Once you choose the q's, you've got the d by dq's, you've got the dq's, and then you've got the p's. The p's are just the coefficients of the base, in terms of the basis.
Mhm.
So this is why these p's are called the canonically conjugate variables to the q's. It's because the way they're thinking is that the q's have already been chosen, and they determine the p's. And there's one p associated to each q.
Okay,
Does that make sense?
I think so.
So the problem is that, like, the reason that I posed the problem in the question, in the assignment, is that I'm basically I'm basically kind of trying to implement this where, if I give you a submanifold, a surface inside 3 space, inside R3, right? Then there's various ways that you know of to choose coordinates on that surface. And I gave you one possible way. It's not a usual way. Normally they would take, let's say, theta and phi, the spherical coordinates. Okay, but it doesn't, this thing that I'm saying about configuration space and coordinates, it does not care what coordinate system you use. You just call them the q's. So this could be theta and phi, it could be x and y, it could be y and z. It doesn't matter what it is. Okay. So whatever the coordinates are that you're using on the sphere, they will impose coordinates on the phase space, on the cotangent bundle of the sphere. And the point is that those are more difficult to determine than just using the fact that the sphere is sitting inside R3. You need to actually look at this basis, the dq basis, and compare that basis to the basis in R3. And you can kind of express you see, like, I'm basically giving you 2 descriptions of the cotangent space, and I'm asking you to compare them. So just pick a point on the sphere. That's the point x in the in problem C. I have TS2. The tangent of S2 is xy such that x squared. Right. So pick a point x, and then you look at the tangent space, which is the set of all y such that x dot y is equal to 0. Right. So I fixed a point on the sphere, and then I look at the tangent space, and that tangent space is being described to you as a subspace of R3. It's the set of vectors y such that x dot y equals 0. So that's one description of the tangent space as a subspace of R3. Now you take that subspace and you take the dual space of that, and that is the cotangent space. Okay, so we have a very explicit description of the cotangent space to a point on the sphere as the dual space of a subspace of R3. Okay, now on the other hand, we have a completely different way of accessing the cotangent space, which does not care about the embedding into R3. It only cares that we have coordinates, q1, q2. Those coordinates give us the tangent vectors d by dq1, d by dq2, and then we have the dual space of that. You see how that does not depend on the embedding because it just uses a coordinate system in 2 dimensions. So the question is all about identifying those 2 things. If I give you a covector in terms of this kind of embedding into R3, or if I give you a covector in terms of P1, P2, you need to identify them.
Okay.
So it's basically it's a slightly tricky change of variable problem.
Okay. Yeah, I'll try to give that a try.
Okay.
Thank you.
You're welcome.
just a quick question about the same problem.
Yeah.
I did it for the thing for the upper sphere. Is that okay if I don't do it the lower sphere because it's just a sign change? But typing everything up again in LaTeX would be a little painful.
Everything is the same, but a sign change. Then why don't you just say for the lower sphere, everything is obtained by setting this to minus this.
Okay.
It takes one line. If it's something is easy, then it's easy. If
Okay.
you are doing something easy and you're writing it to be complicated, then you're working for no reason.
Okay.
Something is simple, it should be simple.
Okay. I'll make sure to do that.
Yeah.
It's just silly. I just came to my mind.
That's all right. I don't mind.
Fully processed.
Making simple things complicated is a hobby of most people.
I have a question about if I'll let other people go first actually because I already
Yeah,
asked.
is there anyone else who has a question? I really thought that today was the 2-hour class. Oh well.
There is a question actually in the chat, I think, before we move on.
Okay.
Someone
Sorry, how does the inner product identify the tangent and cotangent spaces? Well, okay, so if you if you have a vector space, let's say this is a real vector space, and we have an inner product. This is a non-degenerate symmetric inner product, or non-degenerate symmetric bilinear form. Then any element in the vector space can be sent to a linear function on that vector space, namely this. You could call this L sub x. X is sent to Lx. Lx is a linear function on the vector space because if you feed it any other vector y, it will give the inner product between x and y. So each vector is sent to a covector. And so this defines an isomorphism between the vector space and its dual. Okay. And then if you have a subspace of V, then you can restrict this thing to the subspace and you get a dot product, or you get a inner product on the subspace. This is a non-degenerate symmetric bilinear form on the subspace. And so this thing will do the same thing. So you can see that for the sphere, right, the fact that I have the dot product on R3 means that every tangent space will be identified because it's a subspace of R3, and because R3 has this inner product, it means that every subspace of R3 will be identified with its dual, just because I can restrict the dot product to every possible subspace. So that's a very powerful thing, that, you know, if you have a vector space with a dot product, any subspace of it will be identified with its dual in a natural way by the inner product. I mean, you should have learned this this basic fact about identifying the vector space with its dual. Oh, by the way, what I'm talking about here is a finite dimensional vector space. Of course, it could happen also for infinite dimensional spaces. For Hilbert spaces, it will happen, but there are some infinite dimensional vector spaces where it does not happen. But anyway, is this okay, or do you want clarification on this? That's fine, as you like. And also, you should figure out a way to make your video work in the future, because it's good if I get to know you guys. Because if I have to write a letter for you or something one day, then it'll be a lot more possible for me to do it if I can see you and associate your name to your face and so on. I don't mind if you have cats running all over you. That's fine. Don't be embarrassed.
Probably better.
I had a question about thinking about this tangent spaces. Sorry, excuse me. So we're talking about the Lie algebra. That's the tangent space at the identity on the Lie group, right?
Yeah.
And so if I'm understanding correctly, if we just have some general Lie group, right? We
Yeah.
want some principled way to lift vectors from the Lie algebra to the group itself, and for example, by like the exponential map for the matrices, some equivalent map, and
Yeah.
then we pick the commutator of those lifted vectors or whatever.
Yeah. Once you if you have two vectors, you're talking about the Lie bracket. You have
Yeah,
two.
yeah,
If you have
yeah.
two vectors in the tangent space to the identity, then you can propagate those to paths, and then
Yeah.
you take the group commutator of those. That gives you another path, and then you differentiate that path. So the process is exactly as I described.
Right.
The only thing that is not obvious is for a general Lie group, how do you define the exponential map?
Exactly. That's what I was wondering. So
Yeah.
that you said as a proposition, you stated there exists such a map that we can
Yeah.
do reliable kind of thing. But okay, that's just what I wanted to make sure I was understanding that.
Yeah. So it's not obvious how to define the exponential map in general. Some people, what they do is they use the fact that any Lie group can be embedded into a matrix group, and then they use the exponential map for that. But then you need to show, if you use that definition, you need to check that if you embed it in different ways, that the exponential matrix, the matrix exponential, will agree in both cases. There is a kind of direct way of defining the exponential map, but so actually defining the exponential map is let me see if there's a nice easy way to do it. Yeah, there's a way to reduce it to the flow construction that I talked about before. So basically, it proceeds in the following way. So you see how we discussed just a few moments ago, we talked about how the tangent space to the identity can actually be identified with the tangent space to other points.
Yeah.
So if you give me a vector in the tangent space to the identity, I can take that vector and I can transport it, let's say by left translation. I can transport it all around the group.
So using the push forward for the differential of the
that's right.
Okay.
Using the derivative of this left translation map, I can drag this vector around, and I'll get a vector field on the group.
Okay. Yeah.
And then what you can do is then you can try to find an integral curve. So if you specify,
and then that's our path. If we find that integral curve, given an initial condition.
Yeah. Yeah. The problem is that this way of describing it doesn't show that it is smooth. But yeah, you can do it this way. You can convert it into a problem of integrating a vector field along finding an integral curve which goes from the identity, starting from the identity, and then you'll be able to produce your one parameter subgroups. And that basically reduces it to an ordinary differential equation that you have to solve. So finding the exponential map ends up being the solution to an ODE with initial conditions. So you can kind of see how that works. If you there's a very beautiful book by Doistermaat and Kolk, which goes through this in great detail, and they wrote it for undergrads, with undergrads in mind. So there's a very beautiful book, Doistermaat and Kolk, on Lie groups. But I don't suggest going through that now. I think it's basically going from the matrix exponential to the general exponential. You're not really gaining anything. You're just gaining enlightenment, but you're not getting anything practical. Yeah.
It's a fun mathematical generalization.
Yeah.
Cool. Great. Thank you.
You're welcome. Someone asked, Neo asked, is it the same as the exponential from geodesic flow? And the answer is not really, because the exponential from geodesic flow requires a metric. And here we don't have a metric. This is a more natural operation. It's more like the flow that I described earlier, the flow of a vector field. The vector fields, they form a Lie algebra, and the diffeomorphisms, they form a Lie group. And the flow is exactly the exponential map. Flowing a vector field to a diffeomorphism, that is the exponential map. Okay, I have to go. I'll see you all on Friday. Bye-bye.